post-print processing, which I simplify in the term of drying, and I have focused this on inkjet processes. We have heard, and I'm focusing my presentation on first principles. That means I'm not talking about products, and I'm not talking about special systems. I'm talking about first principles, what's needed in order to do a post-printing process. And that is when we talk about water-based inks, we have to take into account that it is much more needed in order to get them proper to process further on than removing just the water. And water removal does not mean that I need heat in general. That could be delta P, low pressure vacuum, or could be even freezing, which could also remove the water. We know in the printing business, a lot of that is done with thermal energy. The reason for that is speed and reaction time of these processes compared to the other ones. But if we talk about post-processing, it is not just the removal of the water, it's also the additional so-called humectants which are in there, high temperature boiling solvents, which have also to be removed in these days, not 15 years ago when we were starting with the inkjet. Why? Everybody was using this on high porous materials, and nobody cared about the liquid because the liquid has been absorbed by the substrate. But today, higher speed, higher ink content, covered surface, where's the liquid going? It has to be dried. So if there's no pores anymore there, we have to remove it totally. And then we end up that drying is much more than just removal of the water, because then we have to think about how I get rid of the glycol as well. In addition to that, and I think specifically now for coated materials, the glycol cannot be adapted anymore as much as sometimes people are thinking, because yes, we need to nozzle an open nozzle, but since we have nothing which absorbs the moisture anymore, we have to do other mechanisms which keeps the nozzle open, but not by glycols itself, and therefore other mechanisms in order to get a durable ink is necessary. And depending on the specific applications, there's much more needed when we talk about printed electronics, where we might have a sintering process or other functional systems. But today, my presentation is limited due to the simplicity of what is needed for post-processing to the pure water removal process. In fact, what is also important, and I think I would like to address that, in addition to what Richard Darling told us yesterday, the hype of inkjet and maybe the benefit of inkjet is sometimes limited due to the fact that everybody is talking about the technology, everybody is talking about the versatile and this high optimization and this and that in the ink. And if that not works, then we talk about the high sophisticated Mitsubishi paper. And I think if we build a process, we have to have this optimization based on the different things. And it is, yes, it is technology driven, but we also have to see what is the application process. And if I'm doing a book printing process where that is a totally different process required than if I do roll to roll. And that has to be taken into account. On the other hand side, it's a difference whether I build a label-based digital press, total 30,000 euro. A dryer with 30,000 euro would not do the job, right? So therefore, the solutions which are needed are pretty much dependent on the budget I have. That was only for the introduction. Now, we talk about drying, and if we say it just has to be dry, then we might see this as an answer. But I think everybody would agree that there is a different stage of drying maybe to be addressed, and that's why I'm talking about. Before we talk about the drying, we should talk about what we apply. And here we have to take first, water-based inks are low viscous and therefore are high liquid containing, and sometimes up to 90% water. And therefore with my simplifications, I take just wet film is equal water. But we start with paper. Our typical paper, 100 grams, 5% ambient moisture, means we have 5 grams per meter square water freight. I have here 1 meter square as paper, the white one. These are 5 grams water. That is the content of water which is absorbed in that paper under saturated ambient conditions. Yeah? Now we talk about what is applied on the substrate. And also typically one printhead can adapt something like 5 grams of liquid through the nozzles. Again, you see here yellow 5 grams, magenta, and if you put them all together, you have the same amount of what is in the paper you add in up to the printed area, at least up to 300% is pretty often, in some extreme cases even 400%. And on the other hand side, since we know there are primers involved, so we talk another 2 grams per water, so overcoat 5 grams per water. Even in order to keep the nozzles in operation, spit bar printing every 300 millimeters over a meter means that we talk about 0.3 grams per meter square printing of ink per meter. And that means that is already 6 to 7% out of the content of the application of that. And that is only in order to keep the nozzles open. Here I have done some data for different inkjet systems, 1 meter per second, 1 meter wide, and you see what are the grammages per second to be removed out of the system. And the reason why I like to focus on the bigger ones is because that represents decoration of water removal. That's this you have to try in a second. And if you go even to the case of the fastest, biggest inkjet printing device today, that is 3 meters and 5 meters, that's the HP 1100, we talk about 200 grams of water to be removed per second. That is this. If you add the primer and overcoat for that, we talk about more than 300, and that is per hour 1 cubic meter of water to be removed. And if you take this into account, I think we chose that the removal of that process is crucial for the overall process. And if we now take into account that out of these 100 grams per second liquid, up to 50% is humectants, which is far away from the evaporation point of water, we are in the problem of what, why, and how the drying technology can be applied. And therefore, if you have, and that's another point, this is the water content of the paper, which is running with 5 meters per second at 2.8 meters wide. They are 292 80 grams papers per second to be run through. That means we are operating with 5 tons of paper per hour. And if you have now a process in drying which takes place to say I heat up the substrate, there's a lot of energy you need just for heat up the substrate. And if you say during my process I remove up to 4 grams, 4% of my water out of my system, That is what you have to remove in addition, and the energy to take. And now we talk about the drying systems, and that is what we have seen in the other presentations, more or less in different descriptions. Let me focus just the following. When we talk about drying, we have to take into account that there has to be energy transferred and the moisture has to be removed. So therefore, the hot air dryers are the only ones which are properly defined as a dryer, because the air is used as heat transferred, as well as because of the ventilation removing the moisture inside of the chamber. If we talk about the other systems, like a conduction system, it's just a pure, simple, stupid heating device, like my iron, and that means in order to get a conduction-based system as a dryer, I need something which removes my moisture. And the same is with the radiation systems, and that has to be learned in the business for the last 20 years, more or less, and today has been reflected and respected in the earlier presentations. But when I talk about the radiation-based heating devices, I think I would also distinguish the advanced near-infrared technology, which is a little bit different to the other processes which I will line out in a few seconds. As I said, heat convection is a process in conjunction with the air as a drying process. But what we see, since we are driven by the delta T of the heating up of the substrate, so my media to heat up that, as well as how far my heat transfer is given. And this shows you immediately, based on what is possible. Delta T, if I'm pretty optimistic, can 250 watt per meter square, and Kelvin, I'm also already pretty optimistic. And that means that a heat transfer drying system based on convection requires several meter squares. And if I'm talking about a drying area of 14 meters square per second, you can imagine that that would mean, and that is describing why we have this large size air dryers in the media. On the other hand side, if I'm talking about conduction in drying, and we know that pretty simple, I have to do it from the backside. Why? Because otherwise I would destroy my wet surface. So therefore, I have to heat up my full mass of the system and even have a higher temperature from this side, otherwise I don't get heat flow into my system. That means for that little water I take out, I have to heat up my 5 tons of paper fully to get out a small spot of printed. And I could say, that is a meter square. I also have a meter square here. And coverage of maybe, what is it, 20%, maybe 30%. So I have to heat up the full mass of the paper in order to get this little spot to be dried. Again, shows, due to the data, very large areas. And now we are from the radiation. And we will see this maybe similar, maybe a little bit different in the data. But I think what is important, the heat transfer from the higher temperature system to the to-be heated area, and then we have to see what means the to-be heated area. I don't want to heat up the substrate because I want to dry. And what I mean when I want to dry, I don't want to heat the print to 100 degrees C. If evaporation and if removal of water would require 100 degrees C, my clothes, my wife would never dry my clothes in the building, because I've never seen that she heats up my clothes up to 100 degrees C to get out the water. And my dryer in my room is operating with 40 degrees C, maybe with 50 degrees C, but never sees 100 degrees C. So therefore, I think we have to think about that evaporation doesn't mean that we want to boil water. And I think that is important, I want to remove the liquid, and I want to remove mainly the water. And that means the energy I would like to have is in the area where it's printed, and I want to have it absorbed. And now we come to the point of the following, that we have to distinguish between the wavelength emission spectrum that is pretty much dependent, that's true, that's pretty much dependent on the filament temperature, because that describes what is my surface temperature, and at the end, depending on the spectral absorption of my different media. One is substrate, the others are the printed areas, which are the wet inks, wet coatings, and these, yes, every ink is different. But what is the purpose of an ink? An ink, if we simplify this for graphical applications, it is color. And color are driven by pigments. So therefore, I have to think about my absorptive characteristics is whatever, if it's Sequark, if it's Azteca, if it's Sensient, whoever is doing this ink, sorry, I should say also Marabou and yellow from the one or the others. Yes, there is a range of yellow pigments, but if you ask me how many different yellow pigments are used, Mr. de Jonge would answer to me maybe 5, maybe even less. And this is given, at the end of the day, these different pigment groups are used in the absorption characteristics. And there, and I have to say, it is very interesting to talk about absorption data in the area of 5 micron if all my heating sources are driven and shielded by quartz containments. And everybody knows that the quartz containment totally covers any energy above 3 micron. So I don't care what happens above 3 micron. It is only the heat which is then in the containment, and that heat emits with the temperature. But this again is something, if I'm using a lamp, and that cannot be operated above 800 degrees C, because otherwise you have a failure in that, and that means we have a long wave IR heater with very low intensity, and therefore I think we don't care about what happens here. We also are not caring about the UV, even so we have 1% of UV in the high energy density emitters. But what you see here is the absorption characteristics of different papers. Yes, they are different, but there is a generic behavior, and that is true for all cellulose materials. A very low absorption in the visible light, in the near infrared area, and the longer wavelength we come, the higher the absorption in the IR. On the other hand side, there is a high absorption also in the UV, and that is also important for some of the technologies in other application areas to reflect. A similar behavior we would have for plastic, even lower. And if we look, and I think that is important as well, my presenter in front of me was presenting that the measurement of absorption of ink is not easy, but what we have to take into account is that we are not talking about a dry ink, we are talking about a wet ink, and we have to make sure, because of the low thicknesses of what we apply, that we have no interaction of where is it applied. And there's one nice characteristics that the quartz plates we are using have a neglectable absorption at all over the whole wavelength range. And now you see here pigments, and I could use 150 different inks, and I would get, yes, I would get some differences there because of the different pigments to be adapted, but there is nothing above 1500 micron, 1.5 micron, which absorbs anything. The only thing is if I take this now into account, that I apply this on a paper, you see, the ink itself has nothing. And when I get absorption in the longer wave IR, where does it come from? From my paper. the absorption here is higher than the absorption in this area. Why? Because my magenta, cyan, and so on has a lower absorption in this area than my substrate. So therefore, a drying process with longer wave IR always means I heat up the substrate, and because of heating up the substrate, there is an evaporation starting which takes out the water. And if I have an effective drying, if I have an effective moisture removal, then I get a drying out of that. But in this picture, yes, in the near-infrared area, we have a different absorption for the different pigmented systems. In the midwave IR, and that is described to that, the absorption of the non-coated area is the same or higher than the different colors except black. And this is not true for black in general. This is only true for graphite-based black, because the graphite particles absorb over the whole wavelength range. If I would take a black out of a dye, that would look totally white. Here, if someone, and that is, I recognize that as well, that this has been now recognized from one of the lamp manufacturers now as well, that we have absorption bands of water in the near-infrared, even in the visible light, and in the short wave. And in conjunction with high energy density, there is a photonic reaction of these water molecules, which allows us to remove very fast and very effective the liquid, the water, out of the system. And now we come to this point. How are we able to have a drying temperature of 50, 60 degrees C and even get the humectants out, which have a boiling point of up to 300 degrees C? Pretty simple. It is a pure physical disruption process. If my process of removing the water is fast enough, and we are talking about drying times of a tenth of a second, and that means with the water evaporation, with this water vapor, we remove the adapted molecules of the glycols. And that is how we can reach to get some of the glycols out during the pure water evaporation process. Nothing else. Otherwise, you have to do it the other way, put a high temperature on and wait for a long time, then the evaporation also starts. But please let me know how you would like to do this if your material, like a plastic, allows only 60 degrees C or even less. It takes forever to get the humectants out of that. There is not a chance. And that is the other point. If I'm talking about convection, I need time. Convection cannot work in a tenth of a second. Maybe at 1,000 meters a minute at heat transfer, but in the realistic area where we are talking about, convection is neglectable. The only reason why we want to have high velocity impingement air in the process chamber is we want to destroy the boundary layer and we want to remove the moisture out of the substrate and out of the process chamber. And therefore, and this is even a water film of 8 micron thickness, and it clearly shows that there are absorption bands in the system and there is no pigment. Yeah. So at the end of the day, the platform technology based on advanced near-infrared is based on a heating energy system in conjunction with high energy density, and we talk about here large scale 2 megawatt and focused up to 20 megawatt, which is important when I'm talking about direct to shape systems. When I saw a system out of lamp filaments built, and we are talking about a radiation chamber, the reflectivity and the absorbance, which we all have, is whether it's for the air or reflectors, which are not described as a reflector because they are absorbers, then I think the efficiency can be easily seen that we need high reflectors in order to keep a high drying system. And as we have heard several times, the air is important, but in order to get this out, we also have to have the high dynamic adjustable of the system. I don't have to show this. That is systems engineering, which you learn or you don't learn, or you have know-how or you don't have know-how. I think the simple thing is, at the end of the day, what is the energy efficiency of your system? And here you see some principles for what is important, and that is during the drying process, the dry out and the water absorption of the ink is crucial for register. And you see here the difference of if you do this instantaneously or if you leave the system time in order to get some convection, because that dries out the system. So there is almost a magnitude of order difference. If you want to read a book which looks like that, I prefer to go in the sauna, and after 30 seconds I have a book like that. But if I buy it in a shop, I would like to have it like this. And this is whether you do it with hot air or whether you do it with IR. The system is at the end the same, because I heat up my substrate and get my drying product due to that. And therefore, I would like to thank you for your attention, and maybe there are some questions I can answer.
Yeah,
thanks, Mark.
Thank you, Mr. Barr.